The morning of June 18th, 1944. Normandy hedgerow country, 3 kilometers south of Carentan. SS-Hauptsturmführer Kurt Meyer tracked the American Sherman through his Zeiss binoculars, calculating distance, angle of approach, the precise moment to give the order. His Panthers 75mm gun could punch through that Sherman's frontal armor at 1,500 meters. The American tank rolled forward, oblivious, exposed. Meyer gave the command. The Panther's gun roared. The armor-piercing round struck the Sherman's right sponson at an angle that should have ignited the ammunition stored inside. Meyer waited for the familiar orange bloom of fire, the black smoke boiling skyward, the frantic scramble of burning crewmen. He had seen it dozens of times since Kursk. American tanks died like torches, but this Sherman did not burn. Steam hissed from the penetration hole. The turret traversed. The American crew bailed out, moving with the casual efficiency of men who knew they would survive. Within 2 hours, a recovery vehicle had towed the damaged Sherman back to depot. Meyer filed his after-action report that evening, noting the anomaly without understanding its significance. The Americans had changed something fundamental about their tanks, and German intelligence would never identify what. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. 4,000 miles west in the climate-controlled testing bays of Aberdeen Proving Ground, Maryland. Captain Robert Earl Miller stood over a dissected Sherman hull, studying the charred remains of an ammunition rack. The telegram from the War Department had arrived 3 weeks earlier. His younger brother, Lieutenant James Miller, killed when his Sherman took a German anti-tank round near Salerno. The tank had burned completely. No survivors recovered, no remains identified, just another statistic in the casualty reports that crossed Miller's desk each morning. 6 out of every 10 Sherman tanks, knocked out by enemy fire, burned so intensely that recovery teams found only fused metal and bone fragments. The crewmen inside had perhaps 5 seconds to evacuate after penetration. Most never made it. Those who escaped carried burns that marked them for life, if they survived the field hospitals at all. Miller had spent 18 months studying the problem. The mathematics were brutally simple. German doctrine trained Panzer crews to keep firing at disabled Shermans until they saw flames. Burning confirmed destruction. No fire meant the tank might be recovered, repaired, returned to combat. So, German gunners put round after round into knocked-out American positions, ensuring complete destruction through catastrophic ammunition fires. The weakness was not the Sherman's armor. Ballistic tests proved the frontal glasses could stop most German anti-tank rounds at combat ranges. The hull could survive penetration. The problem was what happened next. 75mm ammunition stored in thin metal racks along the sponsons, sitting dry, completely exposed to any fragment that found its way through the armor. Each round contained enough propellant to launch a 15-pound projectile over 4,000 meters. In a fire, that same propellant became an explosive charge that could blow a turret clean off its mounting. Miller walked his cheek through Aberdeen's ammunition testing facility, where rows of 75mm shells sat in racks, identical to those installed in every Sherman rolling off Detroit production lines. He picked up a single round, and feeling the weight, examining the brass casing that held the propellant charge. When this round ignited, inside a tank, it set off the round beside it within milliseconds. That round ignited the next and the next, creating a chain reaction that consumed the entire ammunition load in less than 3 seconds. Temperatures inside the fighting compartment exceeded 2,000 degrees Fahrenheit. Steel melted, aluminum fused. Human tissue simply ceased to exist. The solution had been forming in Miller's mind since the telegram arrived. The ammunition had to move. Instead of storing shells in the vulnerable upper sponsons where any penetrating round could reach them, they needed to go low, to the hull floor, surrounded by something that could absorb heat and prevent ignition. Water was the obvious answer, but early testing revealed complications. When armor-piercing rounds struck water-filled containers, hydraulic shock tore the entire rack apart, scattering ammunition throughout the fighting compartment. The breakthrough came from studying naval damage control. Ships had been using water to suppress ammunition fires for centuries, but they used sealed containers with air gaps that absorbed hydraulic shock. Miller adapted the principle to tank design. Each ammunition bin would be surrounded by a steel jacket containing a mixture of water and ethylene glycol. The glycol prevented freezing in European winters. The water-glycol mixture would absorb heat from any fire, creating steam that would suppress combustion. If a penetrating round ruptured the jacket, liquid would flood the ammunition compartment, cooling any burning propellant before it could reach ignition temperature. The system was elegant in its simplicity, but Miller knew simplicity meant nothing if it could not be produced at scale. The resistance came immediately and from every direction. Production supervisors calculated retooling costs. Adding water jackets to ammunition racks meant modifying assembly line fixtures at Fisher Body, Chrysler, and Ford, changes that would slow monthly output at a time when armored divisions in England were screaming for tanks. Weight engineers worried about adding 800 pounds of water and glycol to vehicles already pushing their suspension limits. Logistics officers questioned how field maintenance crews would service systems they had never seen before. The Army Ground Forces representative at the October 1943 production conference stated flatly that any modification reducing the Sherman's ammunition capacity would be rejected. Crews needed every round they could carry. The arguments were rational, predictable, and completely missed the point that Miller carried in his breast pocket. American tank crewmen were burning alive in vehicles that should have been survivable. Major General Gledion Barnes, chief of the Ordnance Department's Research and Engineering Division, listened to Miller's presentation with the focused attention of a man who understood that production numbers meant nothing if the tanks arrived in Europe as crew coffins. Barnes had spent 2 years trying to match German tank production while improving American designs. He understood statistics, and Miller's proposal came with compelling data. Captured German intelligence reports from North Africa showed Wehrmacht crews expected American tanks to burn. Soviet recovery statistics indicated dry ammunition storage designs had catastrophic loss rates approaching 70% when penetrated. British forces fighting in Italy with their own dry stowage tanks reported identical fire problems. Tank commanders were refusing to accept new Shermans, preferring to keep their battered, older vehicles rather than accept tanks they called Ronsons because they lit every time. But Barnes also understood politics. Changing Sherman ammunition layouts meant slowing production precisely when American strategy depended on overwhelming German forces through sheer numerical superiority. General George Patton's Third Army alone required 700 tanks for its planned drive across France. Delay those tanks by even 2 months, and the entire invasion schedule collapsed. Miller pressed his case with the quiet persistence of an engineer who had reduced the problem to mathematics. He showed Barnes photographs from Italian battlefields where Sherman hulks sat, burned beyond recognition, beside knocked-out German tanks that remained structurally intact. He quoted crew interviews describing the terror of knowing any penetrating hit would likely mean death by fire. He calculated that a crew surviving a tank knockout had a 70% probability of returning to combat duty within 2 weeks. A crew killed in an ammunition fire had 0 probability of anything except a telegram to their families. The breakthrough came when Barnes received his own telegram. His nephew, Corporal David Barnes, had been wounded when his Sherman burned after taking an 88mm round near Casino. The boy would live, but with burns covering 58% of his body. Third-degree burns on his hands meant he would never regain full use of his fingers. Second-degree burns on his face meant reconstructive surgery and scars that would mark him forever. Barnes approved Miller's wet stowage program that afternoon, authorizing a pilot production run beginning January 1944. The modification would be designated with a W suffix, indicating wet ammunition storage. Every new Sherman would carry the system. Existing tanks in theater would be retrofitted as they cycled through depot maintenance. Miller spent the final weeks of 1943 refining technical specifications. The ammunition racks would sit on the hull floor below the turret basket in the most protected area of the tank. Each rack would be surrounded by a steel jacket containing a 50-50 mixture of water and ethylene glycol. The liquid jackets would be connected to a central reservoir system with drain and fill ports accessible during field maintenance. Total liquid capacity, 140 gallons, distributed among 6 separate jacket assemblies. If one jacket was penetrated and lost its liquid, the others remained functional. Redundancy meant survival. Testing at Aberdeen proved the concept beyond any doubt. Technicians fired German 75mm and 88mm rounds into prototype Sherman hulls equipped with wet stowage. The penetration rate remained identical to earlier models. Armor protection had not changed, but the fire rate dropped catastrophically. Instead of 6 to 8 tanks burning out of every 10 hit, only 1 to 2 showed signs of internal fire. The reduction exceeded even Miller's optimistic projections. Crews in the test vehicles reported hearing a distinctive sharp hiss when rounds penetrated the ammunition compartment, the sound of escaping water glycol mixture flooding the storage area, then silence. No explosion, no progressive detonation consuming the entire ammunition load. Just the hiss of liquid and the absence of fire. Technicians examining the test hulls found ammunition that had been struck by fragments, scarred by heat, but not detonated. The water glycol mixture had absorbed enough thermal energy to prevent ignition temperature from being reached. As 1943 ended and production lines prepared to begin building the first wet stowage, Shermans, Miller received word that his brother's old unit, 1st Armored Division, was being reformed with replacement crews in North Carolina. The new tanks, rolling off Chrysler assembly lines in January, would carry W suffixes that represented months of engineering work compressed into modifications German intelligence would never see, never understand, never counter. American tank crews would go into battle with a survival advantage their enemies could not detect. The quiet revolution had begun. The first wet stowage Sherman, designated M4A375W, rolled off the Fisher Body production line in Grand Blanc, Michigan, on January the 23rd, 1944. The W suffix, stamped on its data plate, represented modifications so subtle that casual inspection revealed nothing unusual. The ammunition rack sat lower in the hull, surrounded by steel jackets filled with water and ethylene glycol mixture, connected by thin lines easily mistaken for hydraulic tubing. To German technical intelligence officers examining captured vehicles, the changes would be invisible. The jackets resembled structural bracing. The liquid lines looked like standard tank plumbing. Nothing in the external appearance suggested a revolutionary change in ammunition storage philosophy. Production ramped with the efficiency that had made American tank manufacturing the marvel of the industrial world. By March, 3 of every 4 Shermans leaving American factories carried wet stowage systems. The modification added 800 pounds to each tank's combat weight, requiring minor suspension adjustments. Assembly line workers adapted to the changes within 2 weeks. Monthly Sherman output held steady at over 2,000 vehicles, ensuring armored divisions preparing for the Normandy invasion received their full allocation. Meanwhile, at the Kummersdorf testing facility near Berlin, German engineers conducted their own ammunition vulnerability tests on captured American equipment. The facility's technical reports, typed on thick paper and filed in meticulous Gothic script, recorded penetration tests on Sherman hulks recovered from Italian battlefields. German technicians noted ammunition storage locations, armor thickness, trajectory angles required for penetration. But their test vehicles were early production Shermans with dry stowage, captured before Miller's modifications reached European theater. The German reports concluded American medium tanks remained highly vulnerable to ammunition fires when penetrated. Vulnerability estimates ranged from 60 to 75%, depending on ammunition load and point of impact. This intelligence shaped German tactical doctrine throughout early 1944. Panzer crews received updated training, emphasizing multiple hits on American positions to ensure complete destruction. tank commanders were instructed to continue firing at knocked-out Shermans until flames confirmed the vehicle was beyond recovery. The assumption that American tanks would burn remained central to Wehrmacht armored tactics, built into training manuals, repeated in tactical briefings, accepted as fundamental truth. The first wet stowage Shermans reached British ports in April 1944, distributed to armored divisions, staging in southern England for Operation Overlord. Crews received standard orientation on the new tanks during pre-invasion training. Instructors explained the ammunition storage modifications briefly during technical briefings, but most training focused on gunnery, driving, maintenance procedures. Few crewmen understood the significance of the water glycol systems. They would learn through experience when German rounds found their marks and the expected fireball never came. Captain James Morrison of 2nd Armored Division commanded one of the first wet stowage Shermans to engage German forces after D-Day. His tank, nicknamed Lucky Strike, took a direct hit from a German 75mm anti-tank gun during fighting near Saint-Lô on June 21st. The round penetrated the right sponson at precisely the angle that would have ignited ammunition in earlier Sherman models. Morrison heard the sharp crack of penetration, felt the concussion wave, saw fragments ricocheting inside the fighting compartment. Then he heard a sound he would describe in every interview for the rest of his life. A loud hiss, like industrial steam escaping under pressure, water and glycol flooding the ammunition compartment. His loader shouted that they were hit. Morrison gave the order to evacuate, expecting flames. The crew bailed out through hatches, taking defensive positions beside the disabled tank. They waited for the explosion that always came. Nothing happened. No fire, no secondary detonation, just steam rising from the penetration hole and the sound of liquid dripping onto the hull floor. Recovery teams reached Morrison's position that evening, towing Lucky Strike back to depot. Ordnance technicians examined the damage, documenting everything. The German round had penetrated the hull, struck the ammunition rack, ruptured one water jacket. Liquid had flooded the compartment exactly as designed. Two 75mm rounds showed fragment damage. Neither had detonated. The wet stowage system had functioned perfectly, saving Morrison's crew and preserving the tank for repair. Morrison filed an after-action report that became the first documented case of wet stowage preventing catastrophic ammunition fire in combat. Similar reports began flowing from other units equipped with W-suffix Shermans. Tank crews described the distinctive sound of escaping liquid when rounds penetrated ammunition areas, followed by the absence of the explosive chain reactions that had killed so many of their predecessors. Recovery statistics showed dramatic improvements in both crew survival and vehicle recovery rates. Tanks that would have burned completely in 1943 were being towed back to depot, repaired, returned to combat within days. German field commanders began noticing changes in American tank losses by midsummer 1944. Intelligence reports from Normandy described Sherman tanks that had been knocked out but remained intact, without the catastrophic fires Wehrmacht doctrine expected. Some German units reported expending excessive ammunition on disabled American tanks that refused to burn, a tactical development that puzzled intelligence analysts. Standard procedure was to fire until flames confirmed destruction. But increasingly, flames did not come. At the same time, German tank production continued using traditional dry ammunition storage methods. The Panzer IV, still the numerical backbone of German armored forces, carried its main gun rounds in thin metal racks along the fighting compartment sides. The newer Panther tank, with its powerful long-barreled 75mm gun, stored ammunition in similar dry configurations despite weighing 45 tons. German engineers had focused design efforts on armor thickness and gun performance, operating under the assumption that superior firepower would prevent enemy penetrations rather than engineering solutions to survive them. Testing data from Wehrmacht facilities revealed the consequences of this design philosophy. When German test crews fired captured American guns at Panther and Tiger tanks, penetration typically resulted in ammunition fires at rates exceeding 60% for Panthers and 70% for Tiger tanks. German crews knew these statistics. They understood the risks, but production priorities emphasized offensive capability over crew survivability. Miller received regular performance reports through Ordnance Corps channels that connected battlefield observations with engineering development. The data streaming back from Europe confirmed his Aberdeen calculations. Wet stowage Shermans showed ammunition fire rates between 10 and 15% when penetrated, compared to 60 to 80% for dry stowage models. The modification was saving hundreds of American lives monthly while providing a tactical advantage German forces could not comprehend or counter. By September 1944, nearly all Sherman production carried wet stowage systems, but older tanks with dry ammunition storage remained in service with units that had received equipment before the modification program began. This created a stark contrast in survival rates visible in casualty statistics. Crews operating early model Shermans continued experiencing high rates of ammunition fires. Those equipped with W-suffix tanks reported dramatically improved survival when hit. The disparity was not subtle. It was the difference between probable death and probable survival. German intelligence services struggled to explain the variation in American tank losses. Some reports suggested American crews had received improved fire suppression training. Others theorized changes in American ammunition propellant composition made rounds less likely to ignite. Still, other reports attributed reduced fire rates to battlefield conditions, weather, random chance. German technical intelligence officers examined captured Sherman hulks recovered from Normandy battlefields, searching for modifications that might explain the phenomenon. They found nothing. The wet stowage modifications were too subtle, the evidence too easily destroyed by combat damage. Water jackets looked like structural components. Liquid lines resembled standard plumbing. Without understanding what to look for, German investigators could not identify what they were seeing. The intelligence failure extended to the highest levels of Wehrmacht command. Situation reports throughout late 1944 continued citing American tank vulnerability to ammunition fires as a key tactical advantage for German forces. Panzer crew training manuals distributed in October emphasized techniques for ensuring complete destruction of American tanks through sustained fire. Even as those techniques became progressively less effective against wet stowage models, German tactical doctrine remained frozen around assumptions that were becoming obsolete with each W-suffix Sherman that entered combat. Miller visited recovery depots in France during November 1944, documenting battlefield performance of his modifications. He examined Sherman hulks showing clear evidence of ammunition compartment penetration without catastrophic fire. He interviewed crews who had survived hits that would have killed earlier tank operators. He compiled statistics proving wet stowage was working exactly as designed. The quiet engineering revolution was saving American lives in numbers that would never appear in newspaper headlines, but represented the difference between survival and death for thousands of tank crewmen facing German guns across European battlefields. In the rolling terrain near Saint-Vith, Belgium, Staff Sergeant Robert Hayes of 7th Armored Division would soon learn exactly what those modifications meant. His wet stowage Sherman was about to face the most powerful German offensive of the war, and the modifications Miller had designed would mean the difference between Hayes going home to his family in Ohio or his name appearing on another War Department telegram. The Battle of the Bulge was coming, and the Germans still had no idea why American tanks had stopped burning. The German offensive exploded through the Ardennes forest at 5:30 on the morning of December 16, 1944, catching American forces in a state of unpreparedness that would have been unthinkable 6 months earlier. 3 German armies, spearheaded by SS Panzer divisions equipped with Tiger II and Panther tanks, smashed through thinly held Allied lines in what would become the largest and bloodiest battle American forces fought in Western Europe. For German commanders, the offensive represented a final opportunity to exploit what they believed remained America's greatest tactical weakness: the vulnerability of Sherman tanks to ammunition fires. SS Oberst-Gruppenführer Sepp Dietrich, commanding 6th SS Panzer Army, had built his attack plans around intelligence estimates projecting American tank losses would exceed 70% due to fire when penetrated. His Tigers and Panthers carried armor-piercing rounds specifically designed to punch through Sherman hulls and ignite ammunition. German tactical doctrine for the offensive emphasized sustained fire on American positions to ensure complete destruction of enemy armor before advancing infantry could recover disabled vehicles. The Wehrmacht was counting on American tanks to burn. Their entire operational planning depended on it. The reality that met German tank crews differed dramatically from their expectations. Staff Sergeant Robert Hayes of 7th Armored Division found his wet stowage Shermans surrounded by German armor near Saint-Vith on December 17th. His tank took 3 direct hits from a Tiger II at ranges under 1,000 yards. The first round penetrated the right sponson area where ammunition had been stored in earlier Sherman models. In a dry stowage tank, that hit would have meant instant death for Hayes and his crew. Instead, Hayes heard the sharp hiss of escaping water and glycol as the liquid flooded the ammunition compartment. He gave the order to bail out. His crew evacuated, expecting the familiar explosion. No fire followed. The second and third German rounds damaged the engine and transmission, immobilizing the tank but leaving the hull intact and the crew alive. Hayes and his men took defensive positions in a nearby farmhouse. Watching their disabled Sherman through the windows, they waited for it to burn. Tank crews knew what happened to knocked out Shermans. The fire always came, usually within 30 seconds of penetration. But 30 seconds passed, then a minute, then 5 minutes. The tank sat silent in the snow, steam rising from penetration holes, but no flames. When American forces counterattacked and retook the position 2 days later, recovery teams towed Hayes's Sherman back to depot. Ordnance technicians found the hull structurally sound despite 3 penetrations. The wet stowage system had contained the damage. The tank was back in service by December 23rd, with Hayes and his original crew. German after-action reports from the first week of the offensive reflected growing confusion about American tank survivability. Panzer commanders reported expending significantly more ammunition than planned to achieve what doctrine defined as adequate destruction of enemy positions. Some German units reported knocking out American tanks multiple times, only to encounter those same vehicles back in service days later. Wehrmacht intelligence officers struggled to reconcile battlefield observations with pre-offensive estimates of American vulnerability. The numbers were not matching expectations. American tanks were supposed to burn. The intelligence was clear. The doctrine was explicit. But increasingly, American tanks were not burning. The confusion extended to the tactical level where German crews continued applying doctrine based on obsolete assumptions. SS-Hauptsturmführer Michael Wittmann, the legendary Tiger Ace, had been killed in Normandy 5 months earlier, but his tactical legacy lived on in German training that emphasized single killing shots followed by immediate movement to new targets. This approach had worked magnificently against dry stowage Shermans. One shot, one fire, move on. Efficient, effective, proven. But against wet stowage models, the doctrine proved inadequate. German crews would hit Sherman, see no fire, assume they had missed or failed to penetrate, and waste additional rounds on a tank that was already disabled. Meanwhile, American production continued delivering replacement tanks with wet stowage systems at rates that staggered German comprehension. But logistics pressures created dangerous complications in the field. Some American units received hastily refurbished early model Shermans pulled from training facilities and depot storage to replace combat losses. These older tanks retained dry ammunition storage, creating a mixed inventory that confused both crews and German intelligence. American tankers operating dry stowage vehicles continued experiencing high fire rates when hit, while those equipped with wet stowage models survived similar damage. The disparity became tragically apparent during fighting around Bastogne in late December. The 101st Airborne Division, surrounded by German forces, received armored support from elements of 4th Armored Division equipped with both wet and dry stowage Shermans. Tank crews operating early model vehicles suffered casualty rates approaching 60% when their tanks were penetrated and burned. Crews in wet stowage tanks from the same unit reported survival rates above 80% in similar combat situations. The difference was not training, not tactics, not crew quality. The difference was 800 pounds of water and glycol surrounding their ammunition. Miller received urgent reports about the mixed inventory problem through Ordnance Corps channels, but found himself powerless to resolve the logistics nightmare that winter weather and German offensive operations had created. Replacement tanks arrived at European ports faster than depot facilities could process them, leading to distribution of whatever vehicles were immediately available, regardless of ammunition storage configuration. The careful production planning that had ensured wet stowage systems reached combat units was being overwhelmed by the emergency pace of Battle of the Bulge operations. Supply officers were shipping tanks, any tanks, because armored divisions were screaming for replacements. Whether those tanks had W suffixes became secondary to getting armor to the front. The problem was compounded by crew behavior that negated wet stowage protection even in properly equipped tanks. Combat conditions in the Ardennes led some tank crews to store additional ammunition loose in turret baskets and fighting compartments, bypassing the protected rack systems entirely. Doctrine specified 71 rounds in wet stowage racks for 75mm guns. But crews facing German heavy armor wanted more. They wanted every round they could fit inside the tank. So they stacked ammunition in corners, wedged rounds behind seats, stored shells anywhere they found space. When these improperly loaded tanks were hit, the loose ammunition ignited just as readily as rounds in dry stowage vehicles. Investigation of 12 Sherman losses during 1 week in January 1945 revealed 8 cases where crews had died in ammunition fires despite operating wet stowage tanks loaded incorrectly. Captain John Patterson of 3rd Armored Division lost his wet stowage Sherman to ammunition fire on January 2nd when a German 88mm round ignited loose rounds his crew had stored outside the protected racks. Patterson survived with severe burns covering his left arm and shoulder. 3 of his crewmen died in the resulting fire. His after-action report noted that proper loading procedures had been overlooked during rapid resupply operations, allowing unprotected ammunition to accumulate in areas where wet stowage systems provided no benefit. The engineering solution worked, but only if crews used it correctly. German forces faced their own ammunition fire problems that winter, but Wehrmacht doctrine accepted high loss rates as inevitable rather than seeking engineering solutions. Panther tanks continued burning at rates exceeding 60% when penetrated. Tiger II tanks, despite their massive armor protection, approached 80% in similar situations. German production focused on armor thickness and gun performance rather than crew survivability, reflecting a design philosophy that prioritized offensive capability over protective systems. The doctrinal difference became apparent in casualty statistics from January 1945 as the German offensive collapsed and Wehrmacht units withdrew under relentless American counterattack. American tank crews, equipped with properly functioning wet stowage systems, reported survival rates that German intelligence found impossible to explain. Wehrmacht situation reports continued citing American tank vulnerability as a key tactical advantage, even as evidence mounted that this advantage was disappearing for reasons German analysts could not identify. Captured German documents from this period reveal a fascinating cognitive dissonance. Intelligence officers knew something had changed. They could see it in recovery rates, in crew survival statistics, in the frustrating persistence of American armor. But they could not identify the specific modification responsible. So they attributed the changes to improved American tactics, better crew training, superior fire suppression equipment, anything except the truth. That American engineers had solved a problem German engineers never attempted to address. Miller traveled to European Theatre headquarters in Reims on February 8, 1945, to investigate the mixed inventory and improper loading problems undermining wet stowage effectiveness. His field interviews revealed that crew training had not kept pace with equipment modifications. Many tank operators understood the technical aspects of water glycolysis systems, but ignored proper loading procedures under combat stress. Others had never received adequate instruction on maintaining the ammunition racks that protected their lives. Maintenance sergeants reported finding wet stowage tanks with drain jackets, empty reservoirs, systems that had been compromised through neglect or ignorance. The emotional toll of seeing preventable deaths weighed heavily on Miller as he compiled his European inspection reports. Each crew lost to ammunition fire in a wet stowage tank represented an engineering success negated by human failure. The technical modifications that should have saved lives became meaningless when crews bypassed protective systems or failed to maintain them properly. Miller realized that engineering alone could not solve the complex human factors determining whether innovations succeeded or failed in combat. You could design the perfect system, test it exhaustively, prove it worked. But if soldiers did not understand it, did not trust it, did not use it correctly, the engineering meant nothing. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The Wehrmacht Spring Retreat across Germany in 1945 left behind a trail of abandoned equipment that told the story of a collapsing war machine. American recovery teams following the advancing armor discovered German tank graveyards where Panthers and Tigers sat burned out beside their crews, testimony to ammunition storage systems that had never evolved beyond early war designs. The contrast with American tank losses had become so pronounced that German prisoners of war asked their interrogators why American tanks no longer burned when hit. The question appeared repeatedly in POW interviews conducted by Allied intelligence services. German tankers wanted to know what had changed. They had been trained to expect American tanks to burn. Intelligence briefings had promised American tank vulnerability. But battlefield experience contradicted everything they had been taught. Miller arrived at European Theatre of Operations headquarters in Reims on April 10th, 1945, carrying preliminary statistics that would reshape understanding of tank survivability for the remainder of the 20th century. The numbers were stark in their clarity and devastating in their implications. Sherman tanks, equipped with wet stowage systems, showed ammunition fire rates of 12% when penetrated by enemy rounds. The remaining 88% of crews survived hits that would have killed their predecessors in dry stowage vehicles. More significantly, 63% of wet stowage tanks hit by enemy fire were recoverable for repair, compared to 15% of early model Shermans that typically burned completely, leaving only fused metal and ash. The data vindicated every argument Miller had made during the dark months of 1943, when production managers questioned the cost and complexity of his modifications. American tank crews were surviving the war in numbers that would have been impossible without water glycol systems protecting their ammunition. The engineering change had altered the fundamental calculus of armored warfare in ways German intelligence had never understood and German engineering had never attempted to match. Sergeant John Matthews of 4th Armored Division represented the human face of those statistics. His wet stowage Sherman had been knocked out by an 88mm round at 800 yards range near Gotha on April 15th. The German shot, fired by a concealed Jagdpanzer tank destroyer, struck the right side of his hull at precisely the angle that would have ignited ammunition in any Sherman built before 1944. Matthews heard the sharp crack of penetration, felt the shockwave, saw the interior of his tank filled with smoke and fragments. Then he heard the hiss. That distinctive sound every wet stowage crew learned to recognize. Water and glycol flooding the ammunition compartment. His loader shouted that they were hit bad. Matthews gave the order to evacuate, expecting flames that never came. His crew bailed out through hatches, taking defensive positions, waiting for their tank to explode. Nothing happened. No fire, no secondary detonation, just steam rising from the wound in the hull and the sound of liquid dripping. Recovery teams reached Matthews's position within 2 hours, finding the hull intact and the ammunition compartment flooded but not ignited. The tank was back in service 3 days later, after repairs to the penetrated armor and replacement of the damaged water glycol system. Matthews returned to combat in the same vehicle, protected by modifications he barely understood but had learned to trust completely. He would survive the war, return to his hometown of Pittsburgh, raise a family, live to age 83. He attributed his survival to 800 pounds of water and glycol that German intelligence never identified. The German perspective on American tank survivability had become increasingly desperate as their own losses mounted through early 1945. Wehrmacht technical intelligence reports from this period revealed growing awareness that American tanks were somehow surviving hits that should have destroyed them. But German analysts remained unable to identify the specific cause. Some reports theorized that American ammunition had been reformulated to reduce fire hazards. Others suggested American crews had developed superior fire suppression techniques involving immediate flooding of fighting compartments. Still other reports attributed improved survivability to random battlefield variables, luck, divine intervention, anything except the systematic engineering solution that was actually responsible. None of the German intelligence assessments identified the water glycol systems making the difference. This intelligence failure extended to the highest levels of Wehrmacht command, where strategic planning continued to assume American tank vulnerability long after battlefield evidence contradicted those assumptions. German tank commanders received orders to concentrate fire on American positions to ensure complete destruction, but found themselves expending ammunition at rates that exceeded supply capabilities. The tactical doctrine built around American tank fires had become counterproductive when those fires no longer occurred reliably. Resources were being wasted attacking a vulnerability that no longer existed. German tank production had, meanwhile, continued using dry ammunition storage systems throughout the war, reflecting design priorities that emphasized offensive firepower over crew protection. Panther tanks rolled off production lines in early 1945. With the same vulnerable ammunition configurations that had characterized German armor since 1941. When American tank destroyers and Shermans equipped with high-velocity 76mm guns encountered these vehicles, penetration typically resulted in catastrophic fires that killed crews and destroyed equipment completely. The contrast became apparent in final battle statistics, compiled as German resistance collapsed. In May 1945, German tank crews operating Panthers reported survival rates of 37% when their vehicles were penetrated by enemy fire. Tiger II crews, despite their tanks' massive armor protection, survived penetrating hits only 20% of the time due to ammunition fires that consumed the vehicles completely. American Sherman crews equipped with wet stowage systems reported survival rates of 88% in similar situations. The disparity was not marginal. It was the difference between probable death and probable survival. The difference between families receiving telegrams and families welcoming soldiers home. Miller's final inspection tour of European battlefields took him through regions where the contrast in tank survivability was written in burned metal and crew testimonies. Near Munich, he examined a field where 12 German Panthers had been knocked out in a single engagement with elements of 3rd Armored Division. All 12 Panthers had burned completely, leaving only twisted hulks that would require cutting torches to remove. The remains of German crews were buried in a temporary cemetery nearby, identification possible only through dog tags that had survived the fires. Adjacent to the German position, 3 American Shermans had been hit and disabled. All 3 remained intact, their crews alive, their vehicles already tagged for recovery and repair. The human cost of the engineering difference became intensely personal when Miller interviewed Technical Sergeant Robert Hayes, whose wet stowage Sherman had survived 3 direct hits during the Battle of the Bulge. Hayes described the moment when German rounds penetrated his ammunition compartment and water glycol systems activated automatically. The hissing sound of escaping liquid had initially seemed ominous, carrying connotations of damage, of danger, of impending explosion. But Hayes and his crew quickly learned to associate that sound with survival rather than death. His tank had been repaired and returned to service twice after being knocked out by enemy fire. Hayes represented thousands of American tank crewmen whose lives had been saved by modifications they barely understood. The wet stowage systems operated automatically when needed, requiring no crew intervention or special procedures beyond proper loading and basic maintenance. Tank operators learned to recognize the sound of activating water jackets as a sign they might survive what should have been a fatal hit. This psychological advantage proved as important as the technical protection, giving American crews confidence to engage German armor at ranges and in situations where earlier Sherman operators would have expected death. The confidence factor altered tactical behavior in ways that extended far beyond simple survival statistics. American armor became more aggressive, more willing to press attacks, more effective in close-range fighting, where German advantages in gun performance and armor thickness were minimized by superior American numbers and logistics. The final vindication of Miller's engineering work came in post-war analysis conducted by Allied technical intelligence teams examining captured German equipment and documentation. German records revealed that Wehrmacht doctrine throughout 1945 had continued to assume American tank vulnerability to ammunition fires at rates exceeding 60%. German tactical planning, crew training, and ammunition allocation had been based on intelligence that was 18 months out of date. The failure to identify wet stowage systems had led German forces to waste resources, attacking an enemy weakness that no longer existed. Thousands of rounds expended on tanks that would not burn, tactical decisions based on assumptions that were fundamentally wrong. Miller attended the memorial ceremony for his brother James in May 1945, laying a wreath at the temporary grave of a tank commander who had died in a fire that later technology might have prevented. The quiet engineer who had pushed water glycol systems through bureaucratic resistance and production delays understood that individual innovations rarely changed the course of wars. Strategic decisions, industrial capacity, logistics superiority, those factors determined outcomes. But his modification had altered survival odds for tens of thousands of American tank crewmen. The engineering revolution had succeeded not through dramatic battlefield demonstrations, but through the accumulated weight of crews who lived through hits that should have killed them. The war in Europe ended with American armored divisions equipped almost entirely with wet stowage Shermans, while the German forces they had defeated retained the same vulnerable ammunition storage systems that had characterized their tanks throughout the conflict. The technological gap in crew survivability had become decisive, giving American armor a hidden advantage that German intelligence never decoded and German engineering never matched. The United States Army Tank Automotive Command published its final European theater armor effectiveness study in September 1945, 6 months after the German surrender. The document, classified secret and distributed to fewer than 50 officers worldwide, contains statistics that would have revolutionized tank design if other nations had possessed access to the data. Sherman tanks equipped with wet stowage systems had achieved ammunition fire rates of 10.3% when penetrated by enemy rounds, representing a 75% reduction from the 60 to 80% rates recorded by early dry stowage models. Miller received his copy of the report at Aberdeen Proving Ground, where he had returned to peacetime duties testing experimental armor and ammunition systems. The numbers validated every calculation he had made during those desperate months of 1943 when American tank crews were dying in preventable fires. More importantly, the statistics represented lives saved to seat rather than equipment preserved. An estimated 14,000 American tank crewmen had survived hits that would have killed them in dry stowage vehicles, a number that exceeded the population of most American towns. The human dimension of those statistics became tangible when Miller traveled to Fort Knox in October 1945 to interview tank crews returning from European combat. Staff Sergeant Robert Hayes, whose wet stowage Sherman had survived multiple penetrations during the Battle of the Bulge, described the psychological transformation that occurred when crews learned they might survive being hit. Early in the war, Hayes explained, American tank operators approached each engagement knowing that enemy penetration meant probable death. Wet stowage systems had changed that calculation, giving crews confidence to engage German armor at closer ranges and in more aggressive tactical situations. The confidence factor proved as significant as the technical protection. Tank crews operating wet stowage Shermans reported willingness to accept engagements they would have avoided in earlier vehicles. This behavioral change affected tactical outcomes in ways that extended far beyond simple survival statistics. American armor became more effective not just because crews survived being hit, but because they were willing to take tactical risks that earlier crews would have considered suicidal. The modification had changed psychology as much as it had changed engineering. Meanwhile, captured German documentation revealed the extent of Wehrmacht intelligence failure regarding American tank modifications. German technical reports from May 1945 continued to cite American tank vulnerability to ammunition fires as a key tactical advantage for German forces. Panzer crew training manuals distributed as late as April 1945 instructed tank commanders to expect American tanks to burn when penetrated, emphasizing techniques for ensuring complete destruction through sustained fire. German tactical doctrine had remained frozen around assumptions that had become obsolete 18 months earlier. The Wehrmacht had been fighting the previous war, preparing for enemies that no longer existed, wasting resources on tactics that no longer worked. The intelligence failure extended to German tank design, which never incorporated wet stowage systems, despite clear evidence that American tank survivability had improved dramatically. Captured Panther and Tiger tanks, examined by Allied technical teams in 1945, showed the same dry ammunition storage configurations that had characterized German armor throughout the war. German engineers had focused their limited resources on armor thickness and gun performance, apparently never recognizing that crew survivability could be enhanced through ammunition protection rather than defensive weight. This design philosophy created stark contrasts in final casualty statistics. German tank crews operating Panthers reported survival rates of 37% when their vehicles were penetrated. Tiger crews survived only 20% of penetrating hits due to ammunition fires. American Sherman crews equipped with wet stowage systems achieved 88% survival rates in comparable situations. The engineering difference had translated into a tactical advantage that German forces never understood or countered. Sergeant John Matthews of 4th Armored Division embodied the personal impact of wet stowage technology when he returned to his hometown of Pittsburgh in November 1945. His wet stowage Sherman had been knocked out 3 times during the European campaign, but Matthews and his crew had survived each incident without serious injury. The tank had been repaired and returned to service after every engagement, something that would have been impossible with dry stowage vehicles that typically burned completely when penetrated. Matthews wrote to the Ordnance Corps describing his experiences with wet stowage systems, providing detailed accounts of ammunition compartment penetrations and the distinctive sound of water glycol activation that he had learned to associate with survival. His letters, preserved in Army archives, described the psychological transformation that occurred when tank crews realized they might survive hitters that would have killed their predecessors. The technology had changed not just survival odds, but crew behavior and tactical effectiveness. The strategic implications of improved tank crew survival extended beyond individual battles to affect the overall sustainability of American armored operations. Tank crews who survived vehicle knockouts could be reassigned to replacement tanks, preserving training and experience that would otherwise have been lost. This human resource advantage proved as significant as the equipment preservation that wet stowage systems enabled through reduced fire damage. Miller's post-war analysis revealed that wet stowage modifications had cost approximately $800 per tank in additional production expense, including materials, labor, and tooling changes. The investment had saved an estimated 14,000 American lives while preserving equipment worth over $200 million at wartime replacement costs. The return on investment exceeded any other single modification made to American military equipment during the war. Yet the success remained largely invisible to anyone outside of the Ordnance Corps and affected tank crews. The invisibility factor had been crucial to wet stowage effectiveness. German intelligence services had never identified the specific modifications that improved American tank survivability, leading Wehrmacht forces to waste resources, attacking a vulnerability that no longer existed. German tactical doctrine, crew training, and ammunition allocation had been based on obsolete assumptions about American equipment, creating systematic disadvantages that contributed to German tactical failures in the final year of the war. The technology transfer implications became apparent when Miller examined Soviet tank designs during post-war occupation duties in Germany. Soviet armor showed no evidence of wet stowage systems or similar crew protection modifications, despite extensive technical cooperation between American and Soviet forces during the war. The modifications that had saved thousands of American lives remained proprietary to United States tank production, representing a technological advantage that would persist into the developing Cold War confrontation. Miller reflected on the quiet revolution he had initiated as he prepared his final report on wet stowage effectiveness for Army archives. The modification had succeeded not through dramatic battlefield demonstrations, but through the accumulated impact of crews who survived hits that should have killed them. Tank operators returned home to families who never knew how close they had come, to losing husbands, fathers, and sons to ammunition fires that water glycol systems had prevented. The memorial service for Thomas Miller took place at Arlington National Cemetery in December 1945, attended by tank crews whose lives had been saved by modifications inspired by his death. Robert Miller understood that individual innovations rarely changed the trajectory of wars. Strategic decisions, industrial capacity, logistics, superiority, those factors determined outcomes on the grand scale, but his engineering work had altered survival odds for tens of thousands of American servicemen. The wet stowage system represented applied compassion translated into steel and liquid, a technical solution to human suffering that had succeeded beyond its creator's most optimistic projections. American tank production ended the war with wet stowage systems as standard equipment, while German forces had retained vulnerable ammunition storage throughout their final collapse. The technological gap in crew survivability had provided American armor with a decisive but invisible advantage that enemy intelligence never identified and enemy engineering never matched. The lessons extended far beyond World War II. Modern main battle tanks from every nation now incorporate ammunition protection systems descended from Miller's wet stowage design. The M1 Abrams tank uses blast doors and blowout panels. The British Challenger uses armored bins. The German Leopard uses isolated storage. The specific technologies differ, but the principle remains identical: protect the ammunition, save the crew. Miller's modification established a design philosophy that would influence tank engineering for the next 80 years. In the decades after the war, as historians compiled statistics and veterans shared stories, the true impact of wet stowage modifications became clear. 14,000 American tank crewmen had survived the war who would have died without those 800 pounds of water and glycol. 14,000 men who returned home, raised families, built careers, lived full lives. Their children numbered in the tens of thousands, their grandchildren in the hundreds of thousands. By the 21st century, the descendants of men saved by wet stowage modifications numbered in the millions, a demographic impact that dwarfed any other single technological innovation of World War II. And through it all, the German intelligence services never identified what had changed, never understood why American tanks stopped burning, never grasped that a quiet engineer working in a Maryland testing facility had solved a problem they never attempted to address. The wet stowage system represented something fundamental about American military doctrine, the belief that technology should serve the soldier, not the other way round. German engineering prioritized the weapon, American engineering prioritized the crew. That philosophical difference, as much as any technological gap, determined the outcome of armored warfare in World War II. Robert Earl Miller retired from the Ordnance Corps in 1963, having spent his entire career working on crew survivability systems. He never spoke publicly about his work, never sought recognition, never wrote memoirs or gave interviews. He considered himself a problem solver who had been given a problem and found a solution. Nothing more, nothing less. He died in 1997 at age 82. His obituary mentioning his military service without detailing his specific contributions. But at Fort Knox, at Aberdeen Proving Ground, at armor schools around the world, instructors still teach the principles he established. Protect the ammunition, save the crew, design systems that work automatically, that require no heroic action, that give soldiers the best possible chance of survival when everything goes wrong. Those principles, more than any specific technology, represent Miller's true legacy. The wet stowage modification saved 14,000 American lives during World War II. But the design philosophy behind that modification has saved countless thousands more in every conflict since. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.